Hello and welcome to this lecture on sampling and sampling distributions. After this video, students should be able to describe the aims of sampling and the basic principles of probability, explain the relationship between sample, population, and sampling frame, identify and apply different sampling designs, apply the concept of sampling distribution, and describe the central limit theorem. First, let's discuss what sampling is and why we use it. Sampling is the process we use when we select a sample or a subset of cases from our larger population, our population of interest. And this allows us to infer knowledge and information about our larger population from a smaller sample or smaller group of cases. This is going to save us time and money because then we don't have to go out and collect data on every single case in our population. We can infer or generalize about our population from this smaller sample. And this ends up being more accurate than trying to get information about the entire population. Take, for example, the census. The census takes a lot of time and money, but by the time the census data is collected, a lot can have changed in that time. If we were to look at more transient opinions, say the popularity of a president or something of that nature, by the time we went about and finished collecting data on every single person in the United States, the events and time that has passed means that our data about the popularity of the president would no longer be accurate. So a sample allows us to collect data in a more timely manner to better and more accurately reflect current attitudes about the president. And so this fact of sampling allows us to infer or generalize information about a larger population from a smaller sample, and is the basis for what we call inferential statistics. Again, this idea of inferring or generalizing information about a larger population from a smaller sample. So let's talk about some key terms that we'll need to know going forward. The first is the population. The population is the group of cases that we want to get information about. In the population, there is a parameter, which is the value of a population characteristic that we're interested in trying to measure. Say we're looking at the population of the United States, and we're looking at the ages of the people in the United States. The average age then will be the population parameter, the real, actual age for everybody in the United States. However, we don't want to go out and collect data on everybody in the United States, so we decided to take a sample. And the sample, therefore, is a smaller selection of cases from our target population. And this is where we'll get that information about age. And the average age of our sample then, from this smaller group from our larger population, is going to be the sample statistic. It is an estimate of the population parameter. However, sometimes we aren't able to know our actual population. And so we don't necessarily know who's in our population. We can't necessarily account for everybody in our population. And so we have what is called a sampling frame. It is an operational definition of our population from which we will select our cases. This sampling frame can either be defined by a list. If we have a list of every single person in our population, great, our sampling frame is going to exactly match our population. However, this is fairly rare. We rarely have a list of everybody who is in our population of interest, and so we frequently have to use a rule, such as sending a mailer to every house in a particular area, or sending a mailer to people in a particular address. That is a rule that we're going to use for our sampling frame, and is a lot higher risk because people may have moved. We don't know who exactly lives there, and so there's a lot more room for error to come into our sample than if we have a list of everybody in the population. There are two main types of sampling. There's probability sampling, in which cases are randomly selected and have a known probability of being included in the sample. And probability here is a quantitative measure that a particular event will occur, measured between 0 and 1, 0 being the event will not occur, and 1 the event will certainly occur. And so with probability sampling, we know the chance or the probability of any given person to be selected into our sample, or any given case to be selected into our sample, on a probability of 0 to 1. And this is in contrast to non-probability sampling, in which chances of a given case being selected are unknown and non-random. This lecture is going to focus heavily on what we call probability sampling. Again, sampling where we know the chance or probability of any given case being included in our sample, and typically these are random with one exception. And so the first type of probability sampling we have is a simple random sampling, which is where every possible combination of cases has an equal probability of being chosen. This means that if we were to randomly sample students from a class, each of you would have an equal opportunity or equal chance of being chosen into our sample. Systematic sampling is a form of probability sampling that is not random. This is the exception I was talking about earlier. This is where we have a list of cases and we're going to take every nth person on that list. Say we have 20 people in our class. One way of using this would be to take a list of those 20 people and systematically sample every third person. So the third person would be sampled, the sixth person, the ninth person, 12th person, etc. This can work, but we have to be careful about how our list is organized to make sure there are not any patterns in how the list is organized that will cause problems with taking every third, every second, every fifth, every 10th person on that list. Stratified sampling is when we divide our population into two or more mutually exclusive categories, or what we would call strata. From each strata, we're going to take simple random samples or systematic samples from those stratified samples. And the benefit of stratified sampling is that it allows us to potentially oversample groups that might not be usually included into a sample. So say again we're trying to get a sample of the United States population. If we want to make sure that we get enough people into our sample from indigenous or Native American backgrounds, we may want to use this stratified sampling because Native American or indigenous people in the United States make up only about 0.5% of the people in the United States. And so the likelihood of us getting enough Native American and indigenous people into our sample is quite low if we were to simply do random sampling or systematic sampling. And so instead, by separating out our sample into different strata of different ethnic or racial groups, we might be able to then oversample from a given category, right, from, in this case, Native American or indigenous groups, and so that we have enough cases in that group to make some sort of inference about the larger population. Cluster sampling is when we also break down our population into groups, but instead of breaking them down into different mutually exclusive categories, we're going to do it in a hierarchical fashion. And so population is going to be broken into groups of cases or clusters. Each cluster will then be randomly chosen, and then from within each cluster, cases will be randomly chosen. This is usually done when we do not have a comprehensive list of cases. So an example of that would be if we wanted to randomly sample students from high schools in the United States, or let's say in California. The chances of us getting an extensive list of all the high school students in California is very low. But what we can probably do is find a list of school districts in California. That'll be our first cluster. We can then break those out and select randomly from each of those school districts. And once we have a random selection of school districts, then we can come up with a list of all the high schools in those school districts and then randomly sample from those, and from there maybe get a list of all the students and finally sample students from these randomly selected high schools from these randomly selected school districts. In this case, we've randomly selected at each stage of our sampling, but we did not start with a comprehensive list of cases. So this is what simple random sampling will look like. Each case has an equal probability of being chosen, and we're just going to randomly select from our population. Systematic sampling is when we take every nth person again, and so in this case we're sampling every fifth person. We're going to start with 2, so that means we're going to sample 2, 5, 8, and 11. And now you notice here that none of the blue people got selected into this sample. This is one of the downsides of simple random and systematic sampling, is we might miss groups that we have an interest in within our larger population. And that's where stratified sampling comes in. Here we've stratified our sample into 3 different groups: blue people, red people, and green people. And by making sure we take a sample from each of those groups, we guarantee that we have representation for each of our stratas here. So we have at least one blue person, we have at least one red person, and we have at least one green person in our sample. And so this guarantees us people in our sample, or cases in our sample, that represent groups that we are interested in. Finally, we have this is simple clusters. We've divided up our population into 6 clusters, and we've sampled randomly from 2 of those clusters. This is a very simple form of cluster sampling, and while this can be useful, a much more common type of cluster sampling is this, called multistage cluster sampling. This is similar to what I described earlier. And so if you imagine our list of school districts, H1 would be a random pool of one of those school districts, so H1 is going to be a school district, and H2 will be a school district. And then from the list of high schools in each of these school districts, we're going to randomly select 3 high schools, and so we randomly select those high schools, these P11, P12, P13, P21, P22, P23. These will be the high schools. From these high schools, then, we might be able to get a list of the students in those high schools and start to randomly sample from those students, indicated by these M111s, 112s, 113s, 211s, 212s, 213s, etc. And so that's how we can use cluster sampling to get at individual cases when we don't necessarily have a list of those individual cases by doing this multi-stage cluster sampling. Anytime we sample, we're going to have some error because our sample is never going to exactly equal our population. But how close we get to our population is going to depend on a number of factors. First, how closely our sampling frame here is going to match our population. The closer our sampling frame, which is the operational way we are going to select people to be in our sample, this sampling frame, how close that is to the population is going to be a big determinant of how much error we have. The closer our sampling frame is to our population, the better our sampling error is going to be, the less sampling error we're going to have. Furthermore, whenever we sample, we're going to get some people who don't respond, we're going to get some people who don't participate, and there's a chance that we have a sample that isn't very representative of our sampling frame or population, and that's another set of errors. There's a number of different ways we can get sampling error, and it stems from any discrepancies between our population and sampling frame, how closely our sample matches our sampling frame and population, and then how many of those people we've decided to include in our sample actually respond, and if there's any systematic error in that non-response bias. And non-response bias simply means that is there a pattern to the people who are not responding? Say we're doing some sort of phone-based survey. Well, people without a phone aren't going to be able to participate, and that's going to bias our sample in the same way that people who are at work or not at home at the time we call are not going to be able to answer. And so that's going to be some kind of response error that is going to increase our sampling error. And so this sampling error is a broad category for the amount our sample statistic is going to differ or deviate from our population parameter. Sampling distribution. This is where things get a little trickier. A sampling distribution is a theoretical probability distribution of all possible sample values for the statistics in which we are interested. So imagine we are drawing a bunch of different samples from the same population, all of the same size. If we were to then graph those means, that would be our sampling distribution. And what the central limit theorem tells us is that if all possible random samples of size n are drawn from a population with a mean of mu and a standard deviation of sigma, then as our sample size or n becomes larger, the sampling distribution of the sample means becomes approximately normal, such that the mean and standard deviation of our sampling distribution will be very close to that of the population. And so what this means, and why this is important, is that even if our population is not normally distributed, even if our graph of everybody in our population does not approach that of a normal distribution, if we have a large enough sample, then our sampling distribution will begin to approximate that normal distribution. So if we get a large enough sample size, a large enough n, then the distribution of all the possible sample values will begin to approach that nice bell curve or normal distribution that we're used to. And the importance of this is the fact that as we go along, we will be using this normal distribution and we'll be assuming things about this normal distribution that we can't do unless we assume that our sample distribution begins to approach or becomes very close to that normal distribution. So things like estimation, confidence intervals, regression, ANOVA, chi-square, all assume a normal distribution. And a lot of the data we have isn't normally distributed. A lot of the populations we have are not normally distributed. And so what we can do is use this idea of the central limit theorem to say if we take a large enough sample, then we can ignore the population distribution and assume that if we take enough large enough sample, that our sample distribution, or the distribution of our sample means, will begin to approximate that normal distribution. Some more terms here. The sampling distribution of the mean is a theoretical probability distribution of sample means that would be obtained by drawing from the population all possible samples of the same size. So very similar to our sampling distribution from earlier. Again, through the central limit theorem, we know that as our n increases, as our sample size goes up, the sampling distribution of this mean will begin to approximate normal. It'll begin to show that bell shape, which means that the mean of our sampling distribution will begin to approach the mean of the population. And the standard deviation of our sampling distribution will also begin to approximate the standard deviation of our population. And so the mean of our sampling distribution is calculated the same way as other means, right? Adding up all the means together and dividing by the number of means, or adding up all the values together and dividing by the number of values. But in this case, we are adding up a bunch of means. We're adding up a bunch of sample means and dividing those by the number of sample means to get a mean of all means. I know it sounds a little weird, but it's a mean of means. In other words, alright, that is all for this lecture. I hope it helped. I look forward to talking to you again in the future. Thank you. Bye.